So now, what is the typical task we have to do with antennas? Well, we probably usually don't build individual antennas, but we buy a few antennas and we try to make something useful out of those two commercial antennas. And one idea is to make a broadside array. Say, I bought two identical antennas. Connected simply in parallel. Now I'm not drawing the feed network right now, just the feed point here. Now the question is, what spacing is the optimum? What spacing here for what? For the maximum. For maximum directivity. At what spacing I should put these antennas to get the maximum directivity out of such an array? And I have two commercial antennas. Okay. One idea is I can measure the element radiation pattern of each antenna. But this is the radiation pattern is in two dimensions, in theta and in phi, and is a complex measurement. It's expensive. Doing it correctly, it's very difficult. So it's very difficult now to find the whole radiation pattern. That's the direction pattern of the array, f of theta and phi, and I can calculate this. But the other radiation pattern, the element radiation pattern, f of theta and of phi, this I can only measure this. And this may be expensive. Measurement is expensive. It's a commercial antenna. I cannot modify. It's just an item I bought in the store. So how to find the optimum spacing between these two antennas? You saw here that this curve I'm just erasing from the board here. This curve was just for omnidirectional antennas, not for antennas that have a radiation pattern. So for radiation pattern, this derivation is actually wrong. This was just to give you an idea what is going on. Now we have to figure out what is the correct spacing between the two antennas. Okay, I can say that this antenna is fed with current I, and also this antenna is also fed with a current I. It's a broadside array, so the currents are the same and in phase, and are of the same magnitude to get the maximum possible directivity. We would like to have the maximum possible gain here. What can I do right now? This is expensive, the measurement. So I would prefer to avoid having anything to deal with measurements of antennas. Also, the one given by the manufacturer is not accurate. So what I can think of first using just one antenna. Using just one antenna, I have power of the transmitter, one antenna, and in the receiver, I have power for the receiver for one antenna. And then I may have both antennas operational. Then I make an array of two antennas. And when I make, this was the first step, in the second step I turn on both antennas, and I get P receiver for both antennas. And for both antennas, how much power do I get? I have twice the currents in the antennas, so I have four times the received power with just one antenna. But this doesn't mean yet that I have a gain of 4 just doubling the number of antennas. I also doubled the power of the transmitter. So I had just a approximately 2, not even that exactly. P transmitter, for the case of 2 antennas, is how much? It's the power in the first antenna. So P transmitter is the power in the first antenna. So let's say this antenna A and this antenna B, or better to call it antenna 1 and antenna 2. It will be easier to write the equations with antenna 1 and antenna 2. So it's the power in the antenna 1 and the power in the antenna 2. Here, if I only have one antenna connected, this is just the P transmitter 1 in the case of one antenna. It's just I absolute value squared times a real part of impedance of this antenna. 1/2, because it's peak values, not, it's 1/2. In the case of 2 antennas, I can describe such a system with the matrix, Z matrix. Z matrix, it's Z11, Z12, Z21, Z22. So the first antenna, how much power does it use? It's 1/2 I times real part of still I squared because it's the same I in both antennas, but real part of Z11 plus Z12. This is for the first antenna, and for the second antenna is 1/2 I absolute value squared, real part of Z21 plus Z22. So this Z here was really Z11 because we had no current in the other antenna, there was no influence from the other antenna. But when I have both antennas operating, I should consider both self-impedances of these antennas and mutual impedances between the 2 antennas. I should consider. And since these 2 are identical, this is identical because the antennas are identical, and these 2 are identical, I could simplify this expression as the power of the transmitter is now equal to twice 1/2 is without the 1/2 sign, I squared, real part of Z11 plus Z21, because the Z12, because the second expression is the same, because the antennas are identical, so this the Z matrix is actually completely reciprocal here and symmetrical. Now, what is the actual gain of this system? The actual gain, so the gain of the whole system, or the directivity of the whole gain of the whole system, divided by the gain of the element. Okay. In the numerator, I have the ratio of the received power. Received power in the PRX in the second case, in the both antenna, divided by PRX1, just one antenna. And in the numerator, I have the increment of the transmitter power. So P total of the transmitter power for both antennas divided by P of the transmitter power of the single antenna. This is actually the gain, because as I said the first hour, the directivity multiplication does not apply. The gain and multiplication does not apply, so I have to calculate. So this case for the one antenna, and this case for 2 antennas operating in our array. And let's see what this happens here. So this ratio up here is equal to 4, because with 2 antennas operating with the same current as the first antenna, I get twice the field, I get 4 times the power. But down here, I should write the powers. And here I have I squared times real part of Z11 plus Z21. And here the double fraction, to solve it, I put this in the numerator, 1/2 I squared, real part of Z11. Just Z11 because we don't have the second antenna, we have no currents in the second antenna, in the case of just a single antenna. So let's see what happens. The I squared cancels out. 1/2 and 4 gives us 2. And we get the following expression. Twice real part of Z11 divided by real part of Z11 plus Z12. So, if there were no mutual influence between the two antennas, so if H goes to infinity, what happens then? If I infinitely space my antennas, then Z12, there is no mutual influence between the two antennas, so Z12 goes to 0, and this ratio, so the increment of gain of the whole array compared to the gain of a single element is just equal to 2. And this is what most people expect. Most people expect to get the 3 dB, the ratio of 2. But in the real case, what should I look? I should look at Z12 minimum. Because Z12 minimum may give me this ratio, G over G element, larger than 2, because if this is negative, the real part of Z12 is negative, this is actually going to be larger because the denominator is smaller. So just drawing here how to get the optimum spacing from the real part of Z12, the mutual impedance Z12, and this will be something like this function. Where is the optimum point? We start with, actually the starting point is here, a real part of Z11, because if the antennas are at 0 spacing, Z11 is equal to Z12. What are we interested in? We are interested in this point here, because here we'll get maximum directivity or gain. The most negative, and this measurement can actually be performed much easier than the whole pattern measurement. This is much easier to perform. It's much easier to perform because we just measure the mutual impedance between two antennas. It's much easier. You can also do it in the lab. You have an exercise to do it in the lab. And it gives you the same result. It gives you, from this mutual impedance measurement, you can see how much gain or directivity you are going to obtain from building an array from two antennas. But even this measurement comes in too large, too expensive. Even this is a measurement, you still require open space to put your two antennas, nothing in front to have no reflections, minimize the reflection, and measure the mutual impedance as a function of the spacing of the two antennas. So this is how things should be done to get it correctly. Of course, you see from this diagram here, because the starting point here is Z11, if you put the antennas extremely close together, you gain nothing from your array. So the other thing here is to make an even simpler way, yet another shortcut, but this is only approximate. And what you have about your antenna, what you know about your antennas, usually you know at least an approximate radiation pattern. So for your antennas, you have some kind of radiation pattern available from the manufacturer. And on this radiation pattern, the information the manufacturer usually gives you, is this minus 3 dB angle. So this is the whole is alpha, the angle of radiation here, from the minus 3 dB point. Now, where is the trick right now? So this was F element of theta and of phi. Build an array so that the arrays has zeros exactly at this minus 3 dB point. So if I plot here now on this figure also the pattern of the broadside array, the broadside array should have zeros exactly in this minus 3 dB point. This should be one lobe of the array, the next lobe of the array, and the next lobe of the array. So it should have zeros exactly at those positions. So should have zeros at an angle of alpha half. If I make the geometry now for my spacing of H, where is this angle alpha half? Now this, the direction here is this, where I should get the zero. And in order to get the zero of the array, this distance here should be exactly lambda half. So this should be exactly lambda half to have the radiation of both antennas here cancel out, because at lambda half they are out of phase. And now we can solve this triangle here. So this is alpha half, actually this angle here. And this is H. Alpha half is also here, alpha half is also here. So H times sine of alpha half should be equal to lambda half. Or in other words, the spacing of my antennas in an array should be equal to sine of alpha. Sorry, lambda half. Lambda half. I made already a mistake. Lambda half divided by sine of alpha half, where alpha is provided, the angle provided by the manufacturer, the beam width of the antenna you bought in the store. And you don't know how it works, you just have this data. And from this data you obtain the spacing, the required spacing to give approximately the maximum gain. But this is a very approximate formula. It may not be correct, but because, why it may not be correct? Because on this diagram, you don't know what are you going to hit here. Are you going to hit this one, or are you going to hit this one, or are you going to hit this one? This formula doesn't tell you that. So if the antennas have pretty high gain, so you are far away in this curve of the mutual impedance, you can get, actually hit the optimum point, but you can also hit the worst point here. So this is usually cited as truth in many antenna books, especially for radio amateurs, but it's actually the wrong formula. It's an approximate formula about that spacing, but you don't know whether you are going to hit here the hill or the valley. You don't know that in advance. So this is sold as a true formula, but it's just an approximate formula. But it's much cheaper than measuring the mutual impedance, and still much cheaper than measuring the radiation pattern. This is far the most expensive. This is the most expensive. Measuring the mutual impedance is somewhere still a measurement. Here is no measurement at all. You just take the data and write it down and put something together. But be careful, you may hit the hill here. Not the valley, but the hill. That's a problem. Oh, we are running out of time. So now, how to make more complicated arrays with more than 2 antennas? There are very simple ways to do that. For instance, we have 4 sources on the z-axis. equally spaced at H. And fed with the same current I, so we are building a broadside array out of this. How are we going to calculate this if this is X, this is Z? How are we going to calculate the radiation pattern of 4 such sources? We first take an array made of the upper 2 sources. And we have the same array down here. And when we have the array of these 2 sources and 2 resources, we further combine them into an array, taking again 2 arrays. So the whole radiation pattern, f of theta and dot phi here, will be the array 2 of 2 antennas at a spacing of, these 2 antennas are at a spacing of 2h. So at a spacing of 2h, I can write it down. This is cosine of, it's a broadside array, so phi is 0. It's k 2h half cosine theta. This is FA2. And then is the array of 2 closely spaced F array 1. It's cosine of kh half cosine theta. And finally, we have our element, whatever it is, our radiation pattern of our element of h of theta and phi, if we know it, or if they were omnidirectional antennas, they are just. But we can simply combine more than one array in one dimension. The same similar reasoning applies if we arrange our elements of our antenna on another axis. That may happen. If we arrange our x, y, z. Say if I arrange my elements at a distance, at a spacing h, on the axis x. What will be now the radiation pattern here? The radiation pattern of this array is going to be cosine of, it's a broadside array, we have no angle, but we have k h half, but here you have cosine theta x. Cosine theta x is actually the angle, so to the general direction r is the angle we measure from the axis x. So it's a spherical theta x is a spherical coordinate system that has the pole in the x direction. Okay, we have the solution here. Now it's just work with geometry to figure out how much this cosine theta x is. And cosine theta x in spherical coordinates, it's actually the x coordinate divided by r. And this is also sine theta cosine phi. So the whole result of this problem is f of the array is cosine of kh half, the same as we had before, but here we have sine theta cosine phi. How do we solve now a problem of 4 antennas in the xy plane? So we have 4 antennas, x and y. We have 4 antennas arranged in a square. Axis z is here, but does not play a role in this problem. Why? We have 4 antennas, all 4 antennas arranged on a square with the side A, and all of them fed with the same current, just to keep things simple, with the same current I. How do we get the radiation pattern of these antennas? Okay, we get one first radiation pattern here. This is F array 1. We have 2 such identical arrays, and this array, F array 1, we know that it is cosine of ka half sine theta cosine phi. But then we have yet another array made of these two arrays, and the other array is this one here. So FA2 is now has two elements but spaced on the axis y. So this is cosine of Ka half cosine theta y, spherical coordinate system with the pole in the y-axis, or if we convert this now to conventional spherical coordinates with the pole in the axis z, we have Ka half times sine theta sine phi. So the whole radiation pattern f of theta and of phi we can combine. Now first the outermost combination, this f2, so this is cosine Ka half sine theta sine phi. Then we have the inner arrays that are arranged in the axis z, so cosine Ka half sine theta cosine phi. And finally we have our element, and we don't know anything about the element, radiation pattern of the element of theta and of phi. Always we use the rule of multiplying radiation patterns. The rule of multiplying radiation patterns always applies because we always met the criteria, so this rule is valid as said the first hour today. So this was f of the second array, f2 of theta, array 2 of theta and of phi, and this was f1, f of the array 1 of theta and of phi. One final problem in this area is, let's see now when we know the radiation pattern of a particular antenna, how to solve that problem. And say we have 4 dipoles in front of a metal screen. Let me draw this antenna. So I explain what I want to calculate right now. I have a metal screen. And in front of this metal screen, I have 4 dipoles, 4 half-wave dipoles. They are all fed in the center. A coordinate system, y-axis is perpendicular to the screen, x-axis lies within the metal screen, x, and the z-axis also lies in the screen. So what is now the radiation pattern of this thing here? First, I will make a side drawing. So a side drawing, a side view is, I have the metal screen. I have here the 4 dipoles. I should see what the spacing is. So the spacing, let the spacing between the dipoles be h. Here, h, h. And let the spacing, the dipoles from the screen, let it be a. Of course, I have the mirror image of this antenna array inside the big metal screen that has minus I the current. It's a broadside array, all dipoles are fed in phase, but I have minus I in the screen, and I also have distance A here. So let's see what we have to solve, which problems. First, it's the element. The element is the dipole, so it's f of an element. F of an element for a half a wave dipole, you remember it was cosine of p half cosine of theta divided by sine of theta. You remember this result from our lecture of the dipole. But these dipoles are not oriented in the axis z, they are oriented in the axis x. So I should add x here, theta x, theta x. Okay? Now I should convert this result to spherical coordinates that have a common z-axis, and with the common z-axis I have cosine of pi half. Cosine of theta x is sine of theta times cosine of phi. And sine of theta x, I can only get it with the Pythagoras theorem, so 1 minus sine squared of theta cosine squared of phi. That's the only way to do it. That's the element, the individual element. Then I have an array of two elements at the spacing h. So this is f array 1. F array 1. We already did that, f array 1. We have it here. F array 1 at the spacing h. This is now cosine. It's a broadside array, so there is no phase difference. kh, h half, cosine of theta. Okay? And that's okay as it is. Then I have two such arrays arranged vertically at a spacing of 2h. I have now the array 2, f array 2, f array 2 is now cosine. At the spacing of 2h, the 2 cancels out, kh cosine theta. We are now here, at this point here. And finally, we have an array in the direction y, because this A goes into the direction, here is the direction y. We have one array here, and its mirror image here. This is mirror image at minus I. Fed in the opposite phase. So what is the solution here? Now here the phase angle phi is equal to p, because it's out of phase. So the f array 3 is now equal to what? Is cosine of p half, because phase angle is p, plus k, h is now 2a here, 2a, half, cosine of theta y, because it's y now our polar axis. So fa3 is now cosine plus pi half is minus sine. I can also invert the sign because it's just enough that I take here the absolute value. So I can write it minus sine of ka, 2 cancels out. Cosine of theta y is sine theta sine phi. This minus sign is unimportant because we usually no, it's not even minus sign. I think it's plus sign. It's okay. Cosine of phi half plus an argument. No, it's okay. It's okay. It's minus sign. It's okay. It's minus sign. So This sign is even unimportant we have here. If we get plus or minus, it doesn't matter really, because we are only interested in the absolute value of the whole radiation pattern. And what the whole radiation pattern is now, the whole radiation pattern, F, is now equal F of the array 3 times F of the array 2, F of the array 2, times F of the array n, 1, F of the array 1, times F of the element. So multiplying this by this, by this, by this, we get the whole radiation pattern of such an antenna. It's just combining pieces together. As long as we get down with the array of 2, and antennas are usually combined with powers of 2, so this is quite typical. Now the only thing we are left for this hour is how do we feed these arrays? How do we feed those dipoles? And there are different possibilities even here how to feed an antenna array. So we may have 3 antennas. I'm just drawing here 3 dipoles, so to keep things simple, not more than that. I may feed these antennas from my generator. I may feed them in parallel, and this is parallel feeding. Via feed lines that have the length L1, L2, and L3. And of course, matching the characteristic impedance of this line. That's another job. So for broadside array, I need L1 is equal to L2 is equal to L3. This is okay from the electrical point of view. The phase difference is 0, whatever the frequency is. But it costs lots of money. It costs lots of feed line. So on many occasions, I feed the elements of an array serially. Not parallel connection, but serial connection. I just bring a line here in between, a line here, and here I connect the generator. This is L12, this is L23. So parallel. Is maximum bandwidth because it does not depend on the frequency, but it's expensive. It's lots of feed lines. Here I have less feed lines, but this thing is frequency dependent. So this is a problem. It's cheaper. This is more expensive. I also have combinations frequently on such 4 dipoles. This thing was used quite frequently in television antennas. Television antennas frequently had 4 dipoles. How they were connected? Well, interestingly, these 2 were cross-connected. Why? And these 2 were cross-connected. There was a reason, because the spacing here was about lambda half. Lambda half of spacing, this is lambda half of line length. This is pi phase angle. If I flip the wires, I get a phase of 0. So this is the trick to get the phase of 0, to flip the wires if they are lambda half long. And I simply connect the generator here in parallel to both groups. And this was a typical solution for television antenna. So combined serial fed and parallel fed. So all this can be done, and all this you can see on the samples. Say like this one here, this antenna is parallel fed. This is 8 elements. Each element has 2 dipoles, one dipole in this direction, one dipole in this direction. So this antenna actually generates 2 polarizations, and it has 2 connectors for each polarization, one individual connector. 8 elements, so these are really dipoles in metal caps. And this is the feed network, so this is still covered. I removed the cover here so to see how it is done. You come with a single cable up here. You split this thing way out. And to get out of the 50 ohms of the supply cable here that comes up here into 850 ohms, you have to do some impedance matching. And impedance matching is done with these quarter wavelength transformers that are covered with a piece of metal sheet here. But this is removed just to see how it is done. So this is a typical 8-element array for a mobile phone base station in the 1.8 gigahertz band. So this is something very, very common today. You see this installed on every tower, on every mobile phone tower, you see installed such antennas. There are also serial fed antennas. Serial fed antennas are built on many occasions with waveguides, like this one here. There are slots, and slots are cut vertical in the broad side of the waveguide. So the waveguide has some current flowing on the side walls, and this current actually feeds this dipole, this dipole, and so on. With the eccentricity, if you had the dipole exactly in the center of the waveguide, it would receive nothing. With the eccentricity of the dipole, you adjust how much current a particular dipole has. After not lambda half, but lambda guided half, the wavelength in the waveguide, you put the next dipole. Of course, to have a broadside array, to have the same phase, you have to install it on the other side. So this has to go in the zigzag fashion so that this has, after lambda g half, this one gets the same phase as this one, and so on. And you have an 8-element array. This was built by a student for Wi-Fi. So this is for 2.4 gigahertz. If you have more complex arrays, okay, there's this array here. This array here has actually 4 patches. I installed this this is for a wavelength of 10 centimeters, 9 centimeters exactly, 9 centimeters. 9 centimeters, so this is an suspended substrate construction. So you see the FR4 only here is quite thin, and you have air down here. Why do you have air in place of FR4? Because air has much lower losses than FR4. So in order to keep losses down, this was such a complicated design with FR4 very thin and air down. It has 4 patches. Each patch has around 200 ohm impedance. This is lambda half, 200 ohms plus lambda half. It's connected to this patch. So 2 patches at 200 ohm, you come to 100 ohm here, 100 ohm here, and these 2 connected together, they bring you the 50 ohm to the connector. So it's also impedance matching is also installed here. This was working pretty good, made in India. You may have both polarizations also on such an array here. You see, this array has 4 patches, but these patches have an additional disk, an additional parasitic element here to increase the gain. An element of 4 patches fed from this point for horizontal polarization and fed from this point for vertical polarization. So this is a trick to have both polarization out of the same array. Beware, because when you big this thing large, you incur into large losses, feed line losses. So this array here is built on a lower loss laminate. It's quite thin, but this laminate here actually contains much of air. It's elastic. If you touch it, it's elastic. And you have here on this array, you have as many as 4. I am correct. I hope I'm correct. You have here 24 patches. 24 patches. And these patches are fed just from one side, but from different sides. Why? Because these patches have the corners cut, 2 of the corners cut. To get the phase shift between this mode, and this gives you circular polarization. So this is this array. It was made for circular polarization with many patches, and the patches themselves are transforming circular polarization into a linearly polarized mode in these feed lines here. Beware of these constructions, these designs, because if you get to a large design like this one here, in this design there is lots of loss in the feed network. These things here may have a radiation efficiency less than 50%. So this is actually a very stupid antenna. This is a very stupid antenna because it has a very poor radiation efficiency because of the high losses in the feed network. Also other such antennas I can show you. Here I have other similar things. Also these patches have even reactive elements on top, but also this one is a very bad antenna because it has good directivity but has bad gain. Here the efficiency is low because of losses in the feed network. The final solution, the most modern if we are talking about, is how to make a steerable array. A steerable array should have each element of the antenna connected to its own electronics. Generating the signal with an adjustable phase. So adjusting the phase, you can adjust the beam of this antenna. And that's the way how antennas of Starlink are made. Of the both the user terminal and of the satellites, Starlink satellites of the satellite internet are being made. Maybe I can send you a link with the movie on some guys in the United States that disassembled those antennas and look at the chips inside and look at the connections of the individual patch elements of those antennas. Those antennas contain, I counted somewhere around 700 chips. They must be quite expensive for production. Now they're selling it at underpriced, so $500 is not the price for 700 microwave chips. This is not the correct price. So, but those antennas are technically really the best you can see today from array antennas. I hope we covered everything about arrays in the limited time we have. I had to make this lecture a little bit shorter because I introduced a very short lecture we are going to have next time on antenna simulation. I had to get the time from the antenna simulations, and in order to get the lectures inside, I had to shorten other lectures. So I have to shorten this lecture about arrays. We could talk a little bit more about arrays here. I had to shorten also the next lecture we have on polarization and on thermal noise from antennas. So I had to recover that precious time to have the possibility to explain something about antenna simulation. For next time, if you want to take part to the lecture, I recommend you everyone to bring with you a laptop computer. I hope we can arrange the power for the laptop computers here. We have find some extension cords for the powers if your batteries are not good. I have programs both for Windows and for Linux, and I will send you a complete zip file containing all the programs. All the programs we are using are free for use, so there is no problem of authors' rights infringement or something like that. So we are only using open software to simulate antennas. It's not as good as commercial software. We will see both. I will describe the theory of both, how are they done. I think I can do that in 1 hour of lectures, and in the next 2 hours you try to follow you simply try to follow the examples I'm showing and programming on my computer on the computer screen here, on the big screen. So this I hope to be able to arrange for next time. It goes a little bit tight, but it's just I'm trying to show you a little bit more. So please think a little about network computers. If you have a good Linux computer with Vine running on it, just every program should work on that. But Vine should be operating on that computer. As on Windows, you can only use the programs for Windows. But there are also good open programs for Windows. That's not a problem, such a problem. So that's it for today.